Today we have with us Professor C.K. So, Professor, Associate Chair, Administration at the School of Civil and Environmental Engineering, Nanyang Technology University, Singapore. He completed his PhD from University of Wales, Cardiff in UK, Masters from MIT in USA, and Bachelor's from Concordia University in Canada. His industrial experience is vast. His work with Noble Denton and Associates in Singapore and McDermott, Southeast Asia Private Limited. He is a member of a lot of professional organizations, including Professional Engineers Singapore, and he is also the Associate Editor at ASCE, Journal of Computing and Civil Engineering from 2003 to 2008. He is also the Honorary Visiting Professor at Shanghai Jiaotong University in China. His research area includes structural connections, computational mechanics, evolutionary computation, smart materials and structures, and journal publications. He's been awarded a lot of prizes and awards, including the Best TCCP Paper Award in 1996, Best Structural Paper Award in 2001, IES, iStruct, Singapore. I'd like you to please bring your hands together and welcome Professor C.K. So.
Good morning, Professor Sharma, the chief guest, distinguished professors, distinguished guests, ladies and gentlemen. It's my honor to be invited by IIT Delhi and Little Mac to share with you all our experience in smart materials, our work in NTU Singapore. But first of all, I would like to acknowledge that our work in NTU started off because of two men from IIT Delhi. One is Ashok Gupta, Professor Gupta, right there, he's sitting right there, and of course the other one is Suresh Bala. In fact, it was Ashok who introduced me to this area because I was still working on genetic algorithm, evolutionary computing. That's the part of what I learned from MIT. Then I was working on it. Then Ashok told me this is the new thing to work on, and he brought in Suresh. So I was just a lucky man. I happened to be there, watch them do the hard work, and then collect all the glory, So thank you very much for the help. Okay, we have this part that I'm describing is we have moved from structural health monitoring to damage prognosis. We want to predict the remaining life of the structures. After monitoring, after knowing they have damage, what are you going to do about it? Not every damage should be repaired. Because my first job was with the McDermott offshore structures. We usually design for 25 years. So if you happen to have found a brace drop off after corrosion, fatigue, do you want to repair it? If it's designed for 25 years, it's already serviced for 20 years. If it can stand for another 5 years, then let's let it service for another 5 years. Don't waste your money and time. Because welding, repairing welding, you have to gouge out the old weld and put on a new weld. And welding is actually fusing of the hot materials. It causes further damage actually. So damage prognosis is important because then we can make a judgment. What is the risk involved? What is the cost involved? What is the cost benefit of doing the repair? Right. So this is our steps right now is into damage prognosis. We have 3 PhD students working on it. This one is using the EMI technique. There are 2 others working using the wave propagation technique. So we're working on them. All right. So basically, the background is just to give some background. Fatigue caused a lot of problems. It's in the 80s, American bridges were collapsing almost once a month. Because the bridges was reaching about 50, 60 years. They built most of the highways and bridges during the Depression years, the 1923s, those are Depression years. So the American government built infrastructures to stimulate the economic growth. They were doing the right thing those days. They put in money to do roads and bridges and all this. But now they find an easier way. They just print money to cause problem for everybody. So anyway, so there were the bridges by the 80s, many of them were collapsing, and because there was not enough qualified inspector to inspect the bridges. And inspecting bridges is very tedious. They have to build the scaffolding. So the guys can go in and look at the underparts and all this. So at the time, the 80s, they came up with expert systems. They tried to build expert systems so they can get ordinary people to use expert system to look at it and make judgment. But that is not that easy. Expert system take longer to build than to train somebody there. Of course, then in the 80s also, there's this classic example of this Aloha plane over Hawaii. It just ripped off the whole top. So, all right. So, it's important to look at the fatigue cracks. It's one of the major structural failure problems. According to ASCE reports, 50 to 90% of structural failure are due to fatigue problem, depending on which stage of fatigue you're looking at. It's caused by materials impurities or accidental overloads. So most of it can be attributed to fatigue problem. And so whether to look at this replacement of components, right? So it's important that we then look into the remaining life to monitor the health, and then from there, once we pick up the problem, then we can make a judgment whether do we want to repair or not. Okay, this just to show some of the conventional health monitoring techniques. We have the local techniques and the global techniques, and then of course the local is highly sensitive but difficult to implement for large structures. The global, they are sensitive to global levels. It's convenient, but more for global levels. So then we will look at the materials, smart materials that we can use to come up with another monitoring technique. Okay, the EMI techniques, which we use most of the time, we are starting to work into the wave propagations. But the Americans group, like under Professor Jujitsu, is ahead of us in this area. Okay, then we also found that they can interface between global dynamic techniques and the local non-destructive techniques. All right, in principle, it's quite similar to global vibration techniques, except the frequency you use can be very high, up to 400 hertz, kilohertz, highly sensitive, just like local. All right, and then the main materials we use are piezoelectric materials, commonly called the PZT materials. Okay, for this particular work by this one PhD student, you look at the experimental test or fatigue test, then you look at the FEM method, numerical simulations, then we came out with a semi-analytical model based very much on the LEFM methods. Okay. PZT, piezoelectric materials, basically like what you can see over there. All right, if you pass through a current, it can elongate, or if you stretch it, it can give you a current. So it can work actually as both a sensor and actuator. And both as a sensor and actuator. And also, the other thing is that because of the actuations, we can actually collect and convert into energy. So I have another group of students, there are two of them working on energy harvesting. Because bridge vibration, the bridge vibrations at our, what we call metro, we call it the MRT station. There are many big crowd of people walking. Then if we can put a damper on top, and when the people step on, it actually generate enough electricity to light up the whole stations. So that's what we are working on. We have a group of students who are trying to build a prototype, get our corporation, MRT corporations to incorporate in the stations, so that they actually save on energy bill. Energy, oil is getting very expensive. So that's the main thing, the basic part of it. So we can actually use for actual actuating, sensing, and energy harvesting. So we have different groups working on this. Our basic principle, when you stretch, okay, and then you can pass out the wave or the signal, and then from there, the response can modulate the current, and we can then receive, because it's actuate and sense, we can receive the signal, and from the signal, we know that if there's any damage, the stiffness will change. The stiffness change, the signal will change. So from there, we compare the baseline, the healthy part, then we know whether there's any damage or not. Okay. So this is an example where we actually have a little beam, where it is a healthy line. All right, then we drill one hole, and then there's 2 holes, 3 holes. You can actually see the shift, the horizontal leftward shift. of the resonant frequency that will give the indication of severity of the damage. Right, basically, then the signature we get here, the conductance and acceptance. Right, so but we found this more useful, especially for fatigue tests because it generates heat, so there is less of a temperature problem for us. So, all right, fatigue. I think most of you know what is this, so I just quickly say. Basically, there are 3 stages: the initiation, which is usually up to 67% of the life. Then once you hit the initiation, the propagations will pick off very fast, and this is almost instant failure after this stage. So these are 3 stages that we try to pick up from experiment, numerical, and our semi-analytical model. From there, then we can do the predictions. All right. So we'll prove to you that actually we can do these 3 stages through the EMI technique. Okay, these are the more the classic method, the SN curve and all this. Well, we are relying on this, easier for us to manage. Okay, and then the experimental test, we actually use 3 specimens using this electric discharge machining method with water cooling the cut, so that you have a consistency in our specimen preparations. And then based on this British codes, this is very much preparation of specimens. And we use this is an instrument testing machine. And then we use the crack detector, which is good for up to 0.02 mm. We can actually detect it at different stages of the test. And of course, we have our pizza team that is bonded, connected to our analyzer, which was sending the alternative current, and then actually get the feedback, and then record it in here, so that at different stages, of course, then we can then see the shift from this healthy stage. All right. So we switch through a frequency range up to 400, a stable for 0.5, and selected stage depending on damages. All right. So for this first specimen 1, 240,000 cycles. At specimen 2, about that, and this is like higher. And the first detectable crack was at 0.02. 0.02 when we first noticed it. That is at the surface, because the detector is, you can only see from surface. There could be an underlying crack already. So at 0.02, and the visible by eyes at 1 mm is 160,000. Okay. This is not detectable by eyes, but EMI technique actually can pick it up. That's the strength of EMI technique. It can actually pick out the incipient cracks very well. Because once you can see, the propagation will just speed up. It goes into the Paris region, it will just speed up. Okay, and then the critical crack was measured at this stage. All right. So this is just some basic things. We use the conductance part because it's highly sensitive to the peak change. All right, and then it's less sensitive to temperature. Fatigue test generates a lot of heat. And we also look at how to quantify the damage. Right? Basically, we look at 3 techniques. One is the reduction in resonance frequency. The other one is the RMSD and the CCMC, which we'll talk about later. Okay, the reduction of selection of resonance peak, we can see that the resonance can be easily identified despite the damage. All right? See, you can see that. You can actually see the change. All right? And every whole spectrum can be used. And that's a good part about this EMI technique, that whole spectrum can be used. And for higher frequency, not recommended because the peaks get too close. We'll see some of these pictures afterwards. All right? At the 160,000 cycles at 1 mm cycle cracks. All right? And then this is a 210 cycle, just critical crack. All right. So this is 120, and then it's 210 cycles. Okay. So we can pick it up very obviously. the baseline. The important thing for experimental results is it must be repeatable, right? To show that we have done it correctly. Because people say, oh, based on numerical, we check the experiment. Test provided experiment, we have done it properly and correctly. So most important thing, we check the repeatability. So it's repeatable exactly at the same spot we get it. All right? And they can be used for other frequency range, but it's not shown here. Okay. Now, using just to show, monitoring the crack propagations. So because to do the prediction, we must be able to monitor the propagations. Then from there, we can then say what will happen next. So you can see that you can actually show this movement. Right? The various different cycles, you can see then there's a big jump here. As we go into the propagation stage, right? Initiation stage, and the propagation stage, then the critical stage. Critical stage, there will be some obvious sign because some peak disappeared and new peaks came up. It's not as consistent as initiations and propagations. So when you see something like that happen, it shows that it's critical stage arriving and it can fail any time. So we can see that as it moves. All right, and then the initiation 1,000 to the 160,000, right? Slight movement, and the rest will move very fast. And from there we can then see the first we'll see the initiations, crack initiations, first 3 peaks. All right, first 3 peaks is 70% of total lifespan. The first is all right. Then the relatively little movement over here, very little movement. Then the second stage, right, up to 1600. It's a major movement over a short span. Then after that is the critical stage. Experimentally, we pick it up, and what we can show is able to identify cells of crack by observing the movement of the peak. From here, we can do our prediction. See, we can actually draw the frequency reductions versus cycles, and the crack length versus cycles. You see the close correlations between them. Right, so from the reductions from this EMI output, we can actually predict the crack length. Right? Initiation stage, propagation stage. And then if we draw almost linear. So if we can detect something here, we can say that after a while, what is going to happen here? Right? Ideally. But please know that it's only under lab test condition. It's not a real big structure. So maybe we need a lot more funding and research to actually apply this onto a real bridge, a real structure. Because real structure is much more complicated than a simple test coupon. But this laboratory test, it shows that experimentally we proven that it's okay, not a problem. The other one is the quantifier. It's quite very widely used is RMSD method, which we found that is not very suitable for this case because RMSD is good for vertical shift, ours are more the horizontal. And then we went on to this, another method. Then we can see there are correlations again, which is a good correlation. All right, and then it's also fancy with changes the shape between impedance natures. Right, this is also another technique. So we compare them with 3. All right, this is more suitable for us. Right, this needs more verification. It's suitable, but still need more study to use this out. So what time we use this? All right, and then the detection of micro cracks. Then the different stages that we need to detect. The micro crack stage, which EMI technique is very powerful for. And then we also need to then look at the propagations. Then we can do the predictions. Okay. These are the micro cracks. At this lower frequency, you cannot really see very much. But when you go to higher frequency, you can see the very obvious shift. All right. So these are identifiable. Okay. For a micro crack, we should go to higher frequency. All right, and then capable of picking out tiny cracks. Highly sensitive, even incipient crack. But when we are looking at the critical cracks, we should not go into high frequency because there are too many of them. Too many of these peaks, then it will become too confusing. So we have to go on to lower frequency. All right, and then at the critical crack stage, relatively damage is relatively minor. Mostly most cycles that no peaks appear or disappear. Yes, before reaching this, and when you reach a critical stage, right, we have some of this that is not very consistent with the previous. So some appear, some disappear. Right? So when we identify this, we know that we have reached the critical stage, and actually experimentally proven. Right? So it's a very good indication of we have reached the critical stage. All right, we also use numerical analysis, numerical study. We use ANSYS. Okay, and we actually model it, 3D simulations. We have PZT. We use these elements. We are familiar with this. So we use this for the simulations. And so because it can also incorporate the piezoelectric effect, all right, and we then went on to refine the mesh, and then we simulate using the uncoupling and all of displacement along the crack. Assume true thickness propagates in straight line. That's our assumption. All right, and for the experiment coupon we can do that, but not for real structures. As you know, when real structures, the way they roll the steel, depending on how they produce the steel. Yeah? So I still have to say that this is good for verifying our experimental results. Okay, and all right, this is very much a simulation, the PZT part. So all right, simulation of EMI technique. Comparing the emitter signatures with the LP results at the LP stage. All right, agreed well. Good match in resonant frequencies. These are experimental numerical results. Good match, conductors, and the conductance, that's the imaginary part. Then we actually have very close match. All right. And then we also shows crack with varying length simulated at this particular 42.2 hertz at the healthy stage. It shows the propagations. All right. And then it actually picks up quite well compared with the experimental that we have shown. I've shown you earlier in the experimental part. Okay, reduction is used. The reduction is then used as a parameter in characterizing crack, because at this stage, this is the best identifier that we can find to use. Okay. So we can actually see this crack movement. All right, and again, show you the reduction versus crack is very similar to the one for experimental. Very similar, except the gradient is not as high. Okay, of course, it has to do with the finite elements. You know, it's an approximation method. It depends on your convergence. Yeah? This finite element method is an approximation method depending on your mesh size. It can be refined. That's what I'm trying to say. So now we go on to the estimations using the linear elastic fracture mechanics. All right, based on remaining crack sections, we can provide better insight to the mechanism of cracks, especially crack propagations. And then the high accuracy is closed form solutions. Okay, but it's unable to consider crack minimization. Right? It's limited to linear elastic minimization. Yeah. Okay, these are very familiar to those who work on fatigue, intensity factor K, and using this, same as what we have used for experimental numerical. Okay, then this is the region. It's not good for picking up this minimization, but it's good for this. The Paris region, the Paris equations. Until here is the critical stage, which we can pick up experimentally very well. Okay, so we actually put this together, all right, and then by substituting the K in, we integrate, we can find the number of cycles that will give us the value. And then in this study, this is the parameters that we built in for the rectangular single cycle loaded in tension. And then after substituting this, we get this. And then this is a critical, K critical, we have this, then we solve. We came up to be very close, 16.7, and this was experimentally what we got, very close. comparing the three methods. Now we compare the three methods. We have this, this, and this. All right. So we compare the three of them: numerical, analytical, special 1, 2, 3. See how well they do. Again, I must emphasize this is lab test conditions. It's good for the first stage with the experimentals. Then we have to go for a more complex stage. Maybe a L shape where the king is. That's the big problem. If we can solve that, that will solve a lot of problems because most of our fatigue crack starts from the connections. Most, if not all, start from connections. If not connections, probably accidental load, indentations, or materials impurity. So mostly the high stress concentrations are at connections. So the next step we want to do is the L shape specimen. Okay, so far so good. It backs pretty well. Okay, and then, all right, fatigue estimations. We come out with semi-analytical solutions. The derivation of semi-analytical solutions for incorporating results from the FEA and this. We check on the 42.2 case. All right, though we have reduction of frequency, number of cycles. Right, results agree well experimental, and we can then use it to predict the remaining life. So if we have something here, then we can say it will follow this curve. Right, it should roughly be around here. How long more can you subject this to the same stress? All right. Empirical solutions. Can use empirical model from this experimental. All right, perform curve fitting. Okay. All right, this is what we can get. Then we can come up with this. Okay. Simplify. Okay, then okay. All right. So quick summary. Okay, 5 minutes. Okay, good. All right. So a quick summary is a fatigue error estimation using EMI technique. All right. EMI technique is versatile in predicting remaining life. So the semi-analytical solution for simple structures combining experimental result data with this we can do. Right. Numerical solutions is useful for the complex. For the more complex one, you have to go to numerical. Empirical, we couldn't produce that. And empirical solutions conducting number of experimental tests. Right? This, using the EMI technique, we can do this. Okay. And then experimental, overall, EMI technique is useful for determining characterizing propagations. Right? As you can see, we can actually see from the reductions of resonant frequency versus crack length. Detections is good for a wide range, can be selected as damage quantifier. These reductions, leverage shift. Actually, from the shifting, we can actually see at what stage already they are in the crack initiation or propagations of critical stage. By looking at the shift. And this could be a possibility, but we still need more work on this. Other observations that we have done, higher frequency, more sensitive to incipient. All right, but for propagations, we try not to use that because there were too many frequencies and then it confused us. And then the critical crack is caused by observing frequency spectrum. Yeah, that's summarize what we've done. MEM methods, right? We use this. Now, that doesn't mean it's the only one. You can use whatever you want. This is a good software to use. And then we can actually the frequency simulator from it match well with the experimental. We have shown it. Okay, simulation of crack propagations and reduction in this did well also. We have also shown from the charts. The two charts are very close, except the slope gradient is a bit different because of the fineness of the mesh we use. We can refine better, but as you know, FDM, there's this convergence. It cannot be totally exact solution. Okay, then we have this LEM methods. All right, we have the semi-analytical solutions. Incorporate this, and we can then use it. All right, by finding the parameters, we can then use it to predict the remaining life. We can use this for the structure constant. Okay, the prediction of the critical crack length. So we use for the experiment verify that, to establish the curve first. Okay. Further studies, all right, I've emphasized several times, is lab conditions, lab conditions. At this stage, very much lab, but lab conditions, we have done the treating well, so we think there's a potential to be used for the real thing. But as you can see, different crack will have different curve that you need to come up with. So it's not that straightforward. Same as an SN curve. Right? SN curve, you have so many SN curve, and then you do an SN curve, you have to do at least 4 specimens. And then specimen can be expensive depending on what type of group. I was from offshore. So a big part of my work was to produce an SN curve for tubular, the K joint, the T joints. Those of you familiar with offshore structures, K, and then the KT joints, they're very complex. To do that is not that straightforward. So this is just a one test. Okay, and then also single crack with known directions. There are known directions because crack is more complicated, depending on materials, depending on how you do the preparation, the rolling of the steel, right? And it will give you other problems. Yeah? All right, so further study is required for larger size, more complex size, and then we also look at wave propagation technique for random crack. For tubes also is a different set of problems. Right? For tube, circular tube, a lot more complex because of torsional waves comes in for the tube. So we have a PhD student working on this circular tube because of the pipeline, the oil pipeline, in case there's crack. And the oil pipeline, when there's a crack, it actually propagates in a long direction because of the hoop stress is double of the longitudinal stress. So when it bursts the wrong direction. So I think 20 years ago there was a pipeline in Texas. It just split one crack is split almost 20 miles and the fire will go on for 20 miles. So how to address some problems? So we have a student working on that. So because of the torsional stress, it's a different set of problems altogether. So we go on to the wave propagation technique. Alright, so we have to look at the probability of crack detections and all the various problems that we have to study for the future. So this is the first stage. And I think there's potential to be developed further, to be actually used by the industry. And it's important for industry that they have something like this. And I think my next talk later, big problem, I think 4 years ago, one of the MRT stations in Singapore, while the excavator machine collapsed. They had monitoring system, but not so reliable and put people with no confidence in what they monitored. They were having results. So many results. The problem with having too many data, after a while we got data fatigue. You don't want to look at it anymore. So they just put it one side and they collapsed, killed 4 people. And that was a big problem. So ours is going to collapse. A good example is the BP, the blow-up preventer was not working, and nobody there to set the alarm because they don't exactly know when it's going to fail because they are unable to predict the remaining time. So these are critical problems. I think there's thank you very much. Thank you.